I would like to get started by saying welcome to everyone. Thank you for joining us for another MassMEDIC webinar. I'm Rachel Robinson, Vice President of MassMEDIC, and it's really wonderful to see you all either for the first time or again. And I really do appreciate you joining us. I know you're going to learn a lot today. This is definitely an interesting topic and something that we as an organization have been wanting to kind of spearhead some efforts towards more engineering focused programs, pardon me, and really outreach and broadening our horizons as far as technical topics go. So I'm so thrilled to be partnering with Jeff Ellis at EWI on this. Just a few notes before I turn it over to him. Remember to keep yourself on mute so we can avoid as much background noise as possible. However, we do absolutely welcome questions. Jeff's going to do Q&A at the end. So if you would type your questions throughout the event into the chat below at the bottom of your screen, we will go through those at the end of the program. So please, as they come up, just pop them into the chat and we'll make sure we cover as many as possible at the end. So with that, I am going to turn things over to Jeff.
Thank you, Rachel. So again, I'm Jeff Ellis. I work at EWI in Columbus, Ohio. I have a strong background in polymers expertise with a PhD in chemical engineering. I've been a senior technology leader here at EWI for less than a year, but have worked my entire career in contract R&D and specifically in polymers for different industries. One of the main focuses of my career has been medical. I've worked with dozens of different medical companies and the polymer issues that they have with their products, both in the early design cycle as well as after something has gone wrong and they need to do that root cause failure analysis. So I have quite a bit of experience in that area. The talk today is how do you avoid medical device recalls that stem from material issues. So more specifically, we will be going into polymers. But before we get there, I'd like to say a little bit about EWI. So EWI's mission is to develop and implement innovative technologies that fundamentally transform our manufacturing clients' businesses. We have 3 different locations. I'm sitting here in Columbus. We have a Buffalo, New York location and a Loveland, Colorado that's just outside of Denver. We have about $40 million in capital equipment, so we have a good amount of test facilities that we can age and test polymers here on site, and we have about 90 plus technical experts. EWI first started in 1984 as a welding institute, and since then we've been adding capabilities as our clients have asked for them. So polymers came into play in the 90s, and we have continued to add the polymers welding and material selection and degradation, failure analysis type tools more recently. But you can see that we have quite a variety of offerings, one of them being modeling and simulation, and this includes modeling of polymer welding is one of our more novel capabilities that we offer. Some of the values and insights that we offer, we are a nonprofit and we are unbiased because of that. We're not selling any equipment, so we're always an unbiased third party when we do project work for our customers, and that delivers improvements in cost, quality, and product performance. We can de-risk and accelerate product design cycle by choosing the best materials, design, and processing. And we can strengthen your technical team. So adding on to your engineering team and bringing in some expertise that maybe your company doesn't have, or just an extra set of eyes that can look at your process, your design, and say, well, have you thought about this? That's what we're really good at, is coming in early and helping think about a problem a new way to make sure that you're going to end up with the most robust product when you field it. As I've mentioned, we like to get involved early in the design cycle. So this graph shows that the cost of change increases greatly as we go from that concept and development through the design freeze and then V&V and product launch. So as we're down in that early feasibility stage, that's where we like to get in, ask the tough questions, do the testing that's going to show that it's going to work, and make all of those changes down in early in that cycle. So then the rest of it can go more smoothly. So if you have a late phase material issue, it can be costly. It's been shown that a recall can cost up to 10% in the drop of a share price. It can be time consuming because you have to do a root cause failure analysis that can take months for the FDA before you can implement a solution, show that that solution works, and get your product back on the market. And it can be common. So 30 to 40% of FDA recalls are related to material issues. So they're things that if we would have thought about them earlier and tested those materials for the environments that they saw, we could have mitigated the issues. So luckily, we can mitigate these failures by selecting the right materials, design, and processing. During this talk, I have 4 different sections that I'm going to go through. So the first one is kind of the methodology of how we think about creating a robust product and the cycles that we go through to get there. The second one is polymer fundamentals, and this is just a few slides long. I want to make sure that everybody's on the same page for discussing polymer backbones and things of that nature, because it will help us understand more of what I'm talking about in the third section, polymer failures. So I'm going to get into polymer failures and show examples in the medical industry of why these things matter. And the last one is I'm going to give you some tools on how do you implement what you've learned in this talk. So how do we make better selections of materials? How can we create a process to do that? So starting with creating a robust product, again, this methodology works for products that are new in the design stage, and it works for products that are out there that maybe they're failing more than the warranty rate, and we need to fix that issue. So let's start with a new product design. We would start down in the left bottom circle there, and we need to think about material selection, design, and process all at the same time. So we have to make sure that all of those go together in concert while we're choosing them. Sometimes we can choose a great design, but then we can't injection mold it. So we're stopped there. Or great, we select the best material ever, but again, it can't be processed the way that we need it to be processed without excessive degradation. So we have to make sure we're thinking about all 3 of those when we're choosing how to make this new product. Then we go up to that top circle, and we can implement that process, material, and design, and we can age it and test it, and we test it by putting it up against stressors that it will see in the environment of use. So this might be things like it needs to go through a sterilization cycle. So let's do sterilization and see how the material fares after that. Maybe it's going to see UV irradiation because it's going to be outside. Maybe it sees high humidity because it's filled with water. So those are things we want to test for and make sure that that product's going to last the lifetime of the product. So once we do that testing, we'll get results from that, and we can see if there's been any degradation or failures. And from that, we can identify the root cause through characterization and understanding. And a lot of times, because we have experience in this area, we can get it right the first time. Sometimes we find unexpected failures that several factors collude together that we didn't expect. And in that case, luckily, we find it early in the design cycle, and we're able to go back around the circles, make the changes over in the process, material, and design, go back through the implement stage, test and age, and come out with something that we know is going to be robust. So mitigating product failures comes down to understanding material properties. And especially for polymers, the material properties are continually changing. They change because of structure, they change because of processing, and they change because of environment. So it's not like we pick the material that we want because of the data sheet, and then those are the material properties for the entire life of the product that you have. It would be much easier if that were the case, but products are really living, moving materials that have moving backbones within them, and they continually change as they see different environments. So a way to come up with how to choose this, and we'll go through this later in more detail, is a requirements document that includes, how do we look at these material properties and how do we test for them? So the design really goes into the structure on here, the macro design. So how tight are the radii of your corners, and will that cause stress concentration later that can cause cracking in your device when it embrittles just slightly? Processing can also go into structure. So if we're talking about microstructure and we have a block copolymer and we have to worry about different regions within that polymer that are soft and hard segments, and do they line up or do they mitigate over time? That would be the microstructure. Processing can induce microstructure. Processing can also induce materials to lose their strength if we go too high temperature and too high shear. So thinking about how processing changes that, maybe we're thinking about how the polymer chains align, and that causes anisotropic material properties. So you bend it in one direction and it's much easier than another direction. And then environment. So this comes back to stressors of the use case, the expected lifetime that it's going to sit at some temperature and humidity, and how much oxidation is it going to see throughout that period. So we'll get into a little bit more detail of all of these, but the keys to creating that robust product are really selecting, aging, testing, and characterizing initial polymer choices, and then understanding how the structure, processing, and environment affect the polymer properties throughout the entire life cycle of that product. Getting into polymers fundamentals here, again, most of you know this, but I just want to make sure we're all on the same page going into the section 3. So what is a polymer? A polymer is many monomers. So mono is one unit. It would be an ethylene here, and an ethylene gets polymerized by the opening of those double bonds between the carbons into single bonds and a long chain. So many monomers get polymerized into the long chain, or a polymer, so many of those units, and it becomes polyethylene. So this is the simplest polymer out there, because it's just a carbon backbone, and that backbone is the carbons that are covalently bonded together. I may call that a chain too. So as I talk through this, think about those carbons being connected as the backbone or the chain. And the side group is just hydrogen on here. So again, that's why polyethylene is the most simple polymer from a molecular structure standpoint. There are different types of polymers. They're classified into thermosets and thermoplastics. Thermosets have cross-linked backbones. So the carbon from one backbone covalently links to the carbon to another backbone. And due to this, thermosets cannot be remelted. They degrade when they're heated. So these are things like your cross-linked rubbers or your silicones that they can't be reprocessed. Once they're in that final shape, if they're heated again, they degrade. Whereas thermoplastics, chain entanglement is what causes them to stay together and be a solid. But as you heat those, the chains become less entangled due to more energy from heat, and they're able to slide over each other. And that's when the viscosity starts to drop, and you're able to turn it into a polymer melt, which is a liquid, and then you can do things like injection molding. Within thermoplastics, there's amorphous and semi-crystalline. Diagram, the lines on it are all the polymer backbones, and the crystalline regions are shown by the ordered areas. So if you see those rectangular sections with all of the parallel lines in them, that is a crystal, because all of those polymer backbones are lined up in a very specific way. The amorphous regions are everything else that looks disordered, all the curly cues on the side. It's just much more random. So semi-crystalline materials have a combination of both, where amorphous materials don't have any of the crystal regions. Amorphous thermoplastic polymers are easy to process. They have broad processing windows because the viscosity changes gradually above the glass transition temperature. Some are transparent. Crystalline materials are not transparent because they have crystals in them which cause light diffraction. And that as that light diffracts, it makes them look white. So you can't find a transparent crystalline material unless it's one huge crystal, which isn't really possible. Some examples of amorphous thermoplastic polymers are COC, polycarbonate, ABS, and PMMA, such as an acrylic. Semi-crystalline thermoplastic polymers are sometimes more challenging to process because they have narrow processing windows. Since they have all of these crystals in there, those crystals tend to melt at a very defined region of temperature. So unlike the amorphous sections that just soften and continue to soften and then melt, this has a very sharp peak. If you do a DSC scan on this, you'll see a sharp peak where all of the crystals melt and the viscosity changes quickly. Some advantages of the crystals are good solvent resistance, increased barrier properties, and increased strength. Decreased creep. So all of these are advantages of why you would want crystals in there. Examples of these are polypropylene, high density polyethylene, polyamide like nylons, and liquid crystal polymers. So that's it for the fundamental section. Just again, getting everybody up to speed as I get into a little bit more detail on why do polymers fail. And before I go into why do polymers fail, I want to say how useful polymers are before I tell you that they fail in these 15 different ways. Polymers are light, they are strong, they are easy to process, they last a long time in the correct environments. If you look around the room that you're sitting in now, I'm sure you can spot 50 different devices that all have plastic components, and that's because they're cheap and easy to use. So those are the reasons why we should use polymers. Now, these are the reasons why we have to be careful when we choose polymers. So in the improper material selection category, we have to worry about things like long-term stress and strain, chemical resistance, resistance from the environment over on the right top there is hydrolysis, oxidation, things like barrier properties. So dynamic stress, we're going to go into more detail with all of the things I just mentioned. Some of the other things that we're not going to get into more detail in this talk, but I wanted to put them on the failure slide at least, are processing. So induced microstructure, something I already mentioned. Maybe we don't understand the different regions of a black copolymer or the orientation of polymer backbones in our product when it gets injection molded. So that could cause high stress if we're not annealing it properly or holding a pack out time for long enough. Improper mold design can also contribute to those things. And then like formulation incompatibility, this can happen with new materials. So if there's not a material that we can find from a supplier that meets all of our requirements, we might end up formulating our own material. And that's when we have to worry about something like a small molecule diffusing to the surface over time and causing differences in the properties to change. So again, these are all ways that I've seen polymers fail, and we'll go into a little more detail. So starting with barrier properties, does your product pass gas? And the answer is yes if you have a polymer. So polymers have enough void volume between the polymer chains that they can actually allow small molecules to pass through them, such as oxygen and water that are already in the air, can diffuse right through and cause permeation of a product like water in or out of your polymer. So even small molecules that are formulated in, like plasticizers or lubricating agents, are mobile within the polymer backbones, and they become more mobile as you warm them up. And over time, you may see these things bloom to the surface. And as a plasticizer comes out, you're going to embrittle that polymer. It's made to make the polymer a little bit more ductile, a little bit harder to break. So as it comes out, you'll see the properties change. And the reason that this happens is concentration and pressure gradients are the driving forces. So if you have water on the inside of something, it's going to have 100% relative humidity when it's sealed, and maybe it's sitting outside in the environment that has low humidity. And that's going to cause a concentration gradient of that high humidity to low humidity through that polymer. Some examples of where this can make a difference: things like secondary molding. The top left corner there is an ultrasonic weld between two polymer parts. And while those parts were already injection molded, then they sat around for a while. And when they sat around, they took up some of the moisture from the atmosphere. And when they did that, that caused then voids in that polymer weld, because that water, when it heats up during the welding process, tries to boil out. And as it tries to boil out, it causes an increase in pressure, and it causes a spherical void within that welded region. Top middle is a syringe that maybe is a high value product that can lose its efficacy due to oxygen permeation. So we all know food can go bad due to oxygen, so we wrap it in plastic that has very good barrier properties from oxygen passing through. Well, the same is true here, where we have to worry about a pharmaceutical product that's yellowing over time because it sat for a year before being used and too much oxygen went through either the seal or the plastic itself. The third one is water permeates out, leaving less volume with higher concentration in a small sealed container. So this would be something that would go into maybe a diagnostic instrument where you're ordering reagent for that instrument and then it's sitting on the shelf for a year. If it changes concentration over that year, then you may be getting erroneous results when you use that for your analytical testing. The bottom left is diagnostic equipment that cycles in pressure can actually cause a failure that's called depressurization explosion. So this is where an O-ring took up too much of helium and hydrogen, too much hydrogen. And then when you release that pressure, it causes nucleation of the bubbles and growth, and then it causes cracks in the seal. So if we're having large pressure cycles or we're holding pressure for a long time and then releasing, we have to worry about that seal taking up too much and then releasing them and becoming supersaturated and causing this failure mode. Another one is powder. So keeping powder dry can be important for a couple different things. Say an aerosolized drug that maybe is for inhalation, and we have to worry about the size of the particles so they get into your deep lung when you inhale that drug. 5 microns is a very good size for that. Now, if water can permeate through the packaging and cause Oswald ripening to enlarge those particles, now we're not going to get the same efficacy. We're not going to inhale it deep into the lung. Similar with dissolution for a reconstituting syringe. So if we have a dry powder in there that then we are dissolving before we inject it, which I've seen more and more of these coming out, we have to worry about keeping those particles the same size. So the dissolution rate happens before the injection. The last one there is a car dashboard, and that shows the plasticizer coming to the surface and embrittling that plastic. So I mean, that's one that we've all seen, we're all privy to. So the testing, permeation can be measured, and it can be measured using a device shown on the right there, where you put a film sample in the middle, and then you have, say for water, you have one side that's water vapor is coming at a very high relative humidity, and on the other side it stays dry, and then it goes to a detector to detect any water that goes through the film itself. So things that matter: polymer type, surface area, thickness, temperature, relative humidity, and time. Some recommendations for what to think about during barrier properties. If you'd like to enhance barrier properties, meaning you get less permeation through, choose highly crystalline polymers. Add fillers. Fillers act as roadblocks, basically, since most molecules can't go through talc or glass or activated carbon. And choose inert polymers, meaning that ones that, so if you want to have a good water barrier properties, choose one that doesn't like water, that's very hydrophobic, like your polyethylenes. That's why it's lower on this graph in the water permeation, whereas EVOH has that OH group that really is hydrophilic and likes water. So that's why it's an order of magnitude higher on the water permeation. And designing multi-layer materials can be important. So if you want both oxygen permeation and water permeation to be low, you can see a lot of these are like metallized PET. So that's a multi-layer design that can stop both of the molecules from going through. The next topic here is chemical resistance, and you can get embrittlement, cracking, crazing, or discoloration due to any of these four things around it. So hydrolysis can occur when your polymer comes into contact with water, acids, or bases. You get backbone cleavage, and there's some examples there of polymers that are susceptible to it. You can also get oxidation. So all polymers are go through oxidation at some rate, but if it's highly irradiated by light or heated, then by photo or thermal oxidation, it goes more quickly because you get more free radicals to cleave the backbones. So polymers with low TGs are more typically going to have faster oxidation rates. The engineered polymers like PPS and Ultem will have much slower ones. Chain scission can happen due to high temperature, high shear rate, and I'm going to go through an example on the next slide. Sterilization, one type of sterilization is gamma irradiation, and for this you really have to think about what type of polymer you have because it has different effects on different polymers. Chain scission can happen in a PTFE, a Teflon type material, or cross-linking can occur in polyethylene. So two totally different things are happening when you put it in that environment. Some examples of chemical resistance failures here. Top left, transparent polymer becomes hazy after cleaning or disinfecting. Some of the older polycarbonate formulations didn't have very good chemical resistance. Now that has changed and they've gotten better, but maybe you've seen this in the past where you've wiped it down with a disinfectant and then it turns from nice and transparent to this hazy polymer. Top middle is the heat shear cycles that it can induce chain scission. So we have to think about everything that our polymer resin goes through before it gets to a product. And so it's polymerized at the supplier or at the plant. Then the supplier maybe is adding colorant, maybe adding filler in one or two steps. Then it gets injection molded and it gets possibly welded as a final thing. Those are all heat and shear cycles. And each time you go through one of those cycles, you're likely going to lose some strength. So that polymer backbone is going to get a little bit shorter, the molecular weight's going to go down, and you're going to lose some strength. So think about how many cycles yours goes through and try to minimize that. So if you can add color and filler in the same step, or you can do it during polymerization, just creating that so it's the least number of steps is really the best to get your properties close to the technical data sheet properties. Oxidation, this is an example of a housing, a clear housing, and you can see the effect of oxidation over time that cracks have aligned with the polymer chains. So this is an extruded product that then was machined, and you can see that all of the cracks go vertically because that's the way that the polymer chains have been solidified in due to the extrusion process. Bottom left, I already talked about a little bit. Sterilization can have effects on polymers that are completely different depending on the type of polymer, so cross-linking or scission. And then the bottom right one is a little bit different situation where polymer can destabilize the liquid that's in it. So something like a drug formulation may have cresol in it, and some polymers absorb cresol. As they absorb that stabilizer from the formulation actually becomes destabilized, and maybe you'll get crystallization of the drug that's in there, causing the efficacy of that drug to drop. So we really have, it's a two-way street for this, where we have to worry about how the polymer is affected and how the polymer affects any liquid that it's in contact with. Some testing to show if your polymer is going to last when it's in contact with fluids is environmental stress cracking. So here's a setup that you may do where you have rectangular samples that then you put under strain, and then you place fluid on them, and you inspect them at regular intervals for crazing, cracking, discoloration. And this is a great test to do if you're going to be in contact with any type of liquid that there's not already data for. And you can accelerate this testing through temperature, chemical concentration, or strain percentage. You can also do testing. So after you expose a polymer to the environment that it's going to see, you can do testing, mechanical testing on it. And if you see embrittlement, you might see something like this, where the green curve would be the youngest, least aged polymer. The yellow would be middle, and the blue would be the oldest, where the modulus is increasing because it's embrittling. And then you see it breaking at a strain that's less and less. So lower strain, higher stress, increased modulus is something that we look for when we're looking for degradation. Recommendations for getting rid of or taking care of chemical resistance: understanding the products and use environment and contacting chemicals, leveraging the chemical compatibility that's already out there in databases, leveraging sterilization compatibility. So your vendor for sterilization, like Steris, might have something like this. And for untested material and chemical combinations, performing that ESC testing is important. For drug contact, we always want to test in contact for the full life of the product. So worrying about if that drug is going to be just as effective after being in contact for that long. And we can do that through accelerated aging too, to save some time. The third of four different kind of topics that I'm diving into deeper here are polymer dynamics. So this is how polymers change based on how quickly you impact them. So I think the first example I can go through is that everybody's played with silly putty, and we know that it reacts differently when we react to it differently. If you put silly putty on the table and you wait, it flows out more like a liquid. If you roll it up and bounce it, it's more like a solid. That's similar to what's happening here, because we're talking about the relaxation time of those polymer backbones. And we know that polymers are glassy when they're below the glass transition temperature and rubbery above it. And if you look at the data here, it shows that as we impact a polymer faster, so we're going from 0.1 hertz in the blue to 10 hertz in the orange, we see that that TG actually increases. So it becomes brittle at a higher temperature. And for a polymer like polypropylene that has a TG of negative 20 degrees C, if we're also impacting it quickly, now we have to really worry about putting it in a refrigerator and it become brittle at that temperature. Even though the data sheet says that the TG is something, it can be shifted based on how you're interacting with it. Some examples of where this matters: an auto injector that has a spring in it. Maybe you had a smaller spring in there and it worked great for years, but now you have a therapeutic high viscosity drug formulation that's in there, that the medication is higher viscosity. You want to go through the same needle, so you decide to put a larger spring in there. And it looks like it's working fine until you release the energy from that spring. Since it's higher energy, it has higher frequency impact when you release it, which is a lower impact time, and it will cause the polymers to act more brittle. So you could get failure of maybe that white part that pushes on the syringe. The next one, the top right, is the high frequency sensors and devices. So there's a picture of an ultrasound probe there that operates thousands of hertz. And again, we saw the difference from 0.1 hertz to 10 hertz. It went up 10 degrees, and that can continue to go up. So as you go higher in the frequency, you can get an even bigger shift. The last one here is unloading parts from an ultra low temperature freezer. So maybe you put it in the freezer and it was okay in the HDPE jug because it has a glass transition temperature of negative 130. But now as you pull it out and you set it down on the counter and you set it down just a little bit too hard, it cracks because you've shifted that TG just based on setting it down too hard on the table. And now you have a cracked container that's going to leak when it thaws out. Testing for this we can do through time temperature superposition. So about a week's worth of testing, we can get lots of different decades of frequency that we can see what it would look like. So a DMA, dynamic mechanical analyzer, can be used to do this, where you can oscillate a sample in there. And this one, maybe we can't test out to the frequency of our ultrasound device. We can only test up to about 100 or 200 hertz with our DMA. So what we do is we measure them at different temperatures. That's the plot on the left that has all those short curves that are vertically aligned. And we use the time temperature superposition to move those into a master curve. So as we go colder, in this one, it gets superpositioned farther out on the frequency. So if you can visualize moving each one of those to the right, it makes that master curve. So we can, with short tests at varying temperatures, we can create this master curve, and we can show what it's going to act like. Some recommendations on how to avoid this or what to look for. Consider the frequency of planned or potential impacts. So that could include drop testing. So say you have a device that has to go through 1 meter drop testing onto a hard surface. You know, do the calculations on what frequency that is, and then we can discuss, you know, how much that's going to shift the TG and if it's going to crack. Understanding thermal transitions near the service temperature range. So that's back to the polypropylene being just less than freezing and putting it in a refrigerator. And then if you're within 10 degrees C of a transition, that's where we really need to worry about the DMA and measuring that TG shift. So we don't want to cross that TG and go into the brittle region. The last of 4 here are long-term properties. So creep and stress relaxation are a function of design, material, environment, and they stem from the same issue of polymer chains sliding over one another. But there's 2 different things that we're looking for here. So in creep, it's a constant stress. So think of a constant weight on your material and then it changing shape over time. So it's straining as that stays on there. Whereas stress relaxation is a constant strain. So you're holding your part in a certain position for a long period of time, and it pushes back with less and less force. So these failures can pop up years after a build, since they take a long time and they continue to creep or relax as time goes on. Some examples of where it matters, the auto injector again. So that high polymer, high energy spring that's in there is pushing on that little white polymer part, and it with a nearly constant force. So that would be creep, where maybe that small white polymer part is creeping to the point where the keys aren't going to fit into the keyways when you unlock it and go to fire it. Stress relaxation, we can think of an O-ring in a kerf. So we can press that O-ring to make a seal, but over time it takes a set and it presses back less and less hard, and that seal becomes it's less pressure. So maybe you get leaking after years of having that seal in there. Some testing that you can do on this, again, you can use time temperature superposition with stress and strain control. So much like the frequency sweeps, you can do this for stress and strain. And again, in about a week, you can get all of those curves and you can make that master curve, and you can make a prediction that at a certain temperature and at a certain stress, it will creep so much after so many years. So you can see if your product is going to make it the lifetime or the warranty period. And it's a great test to do beforehand. And since it only takes about a week, it doesn't set back your design cycle. Recommendations for choosing polymers that creep or stress relax less. Semi-crystalline polymers are more stable than amorphous due to the crystalline regions that don't creep. Polymers with side groups have less mobility. So that's my pictures over there on the right. Polyethylene has the smallest side groups because it has hydrogen, whereas polypropylene has carbon and 3 hydrogens as the side group. So if you think about trying to detangle Christmas lights, it's like polypropylene. All of those side groups get tangled together and they're hard to slide over one another. So the larger the side group, the less mobility and the less creep you'll get. Higher molecular weight. So this is a longer chain, and as it's longer, it has more interactions with the other chains and it's harder to move. The easy way to tell molecular weight is the melt flow index, which is usually on the tech data sheet. So if it has a lower melt flow index, it'll have less creep later. Fillers typically decrease the mobility and increase the modulus of the polymer. So that also helps with these. And then performing the DMA testing to predict long-term behavior is important if you're going to have constant stress or constant strain on any of your parts. On to the last section, polymer selection process. So how do you use this, this information that we've learned today? So we can use it to create a requirements document. So that's the first step in the polymer selection process. And there are many different requirements that go in the requirements document. One is device requirements, and they're derived from human factors, usability, and functionality studies. So material requirements need to be derived from the device requirements and from other things like life cycle of the device, the subcomponents, the design. So here's a quick example of thermal and mechanical material requirements considerations. We need to consider every environment that that polymer sees from cradle to grave. So your molder gets resin from the supplier and it has some processing temperature that's high shear, high temperature, and we lose a tiny bit of mechanical strength through injection molding. We have to worry about part removal stresses or how the part falls into a bucket and then is covered up by other ones and how much weight is on it. So there's some stress there. Putting it into packaging, is it packaged so that the part has to take the stress or so the packaging takes the stress? How long does it sit? What's the relative humidity? If it's a nylon, how much water is it taking up during that period? Then it gets shipped. So maybe it gets shipped by air cargo, which can be low temperature, low pressure. And what does that do? Maybe if you have a liquid product with a bubble in it and now it's seeing a low pressure environment, that increases the driving force for permeation of your fluid out of the device. And then maybe there's assembly. So you have these secondary operations like ultrasonic welding and laser welding, and that's another heat shear cycle. And then it gets shipped again to the user. And how long does it sit there? Again, what temperature, what humidity, is there irradiations or stresses that the user puts on it? So these are all things we need to think about when we're putting our requirements document together on what does that product need to withstand. And here are a couple examples based on what we've already gone through. I'm running a little bit short on time, so I'll go through just one of these. I'll go through the barrier property ones on the left. So device requirements, that device requirement might say that after 1 year, we can only have a maximum of 1% drop in the efficacy of the delivered drug. Whereas we turn that into the material requirement, and that is oxygen permeation rate, because we know that if oxygen permeates in there, it's going to decrease our efficacy. So we set it up as, well, here's a permeation rate that we have to stay below. And then we choose polymer families that pass that. So there are 3 polymer families listed there that have meet that requirement, that they have permeation rate less than what's shown there. And then we have to worry about what test are we going to do to prove that our product works? Even though it says it on the data sheet, again, we have to prove that the way we process it, our design and our material come together to make it work. So permeation rate testing on our product would be important. And then also testing the liquid efficacy. So that's one example, and there's two more there, but again, I'm running out of time. And of course, there are many other requirements, especially with medical devices like biocompatibility and sterilizability, injection moldable, mechanical, thermal, electrical. So to go through the rest of these steps then quickly, uh, after we create that requirements document, we find polymer families that meet the requirements. So that was those polymer families that I showed on there. We rank to determine top candidates. From that, then we can find specific polymer grades within the top ranking families. And then we can procure chosen polymers and process them into parts, and then we can do our testing to ensure compliance with the requirements. So we have to know what test we're going to do. So I have that right on the requirements document too, of what test are we going to use to prove that this material design and processing worked to meet the requirement. In summary, you can save time and money. You can shorten your design cycle. Actually, if you're doing all of this work up front, the rest of your design cycle should go more smoothly because we've worked out the kinks up front. So we know that product failures are common, costly, and time consuming. We can de-risk that product through rigorous polymer selection early in the development and doing those testing, doing the testing to show that it works in the environment that it's going to see during its life. We can supplement your engineering team. So just, having another set of eyes that's unbiased. We're not trying to sell equipment. Just asking questions of, have you thought about this? Have you thought about that? Are you going to, test it like this to prove that it's going to work? So expertise and testing capabilities are necessary to maximize these benefits. So with that, I'd like to thank you for your time. Thank you for spending this hour with me today, and I'd happy to entertain questions now or private conversation if you have maybe private information you'd like to share so I can help you out. My email address is listed there.
Thanks, Jeff. That's incredible. And we do actually have a couple questions that came in so far. So I will just help read those out to you and we can go from there.
Great.
So one question is, our company's product involves an implantable, flexible polyester mesh. So the question pertains to storage of these devices prior to manufacturing and release to minimize degradation. There's no evidence of degradation, but the person's wondering if there are best practices for storing polyester devices.
Yeah, that's a good question. So polyester isn't too reactive to water like a nylon would be. So I guess I'll go into a little bit of, with nylons or polyamides, you really have to worry about that amount of water that's in the air and how much it takes up. Sometimes you want it to be a little bit more flexible and sometimes you want it to be a little bit more dry, and you have to really balance those things. With the polyesters, you have to worry a little bit less about that, but I would still say keeping it somewhat dry, so not putting it in 100% humidity. If you can keep it in a more reasonable range for relative humidity, and then keeping just the temperature also reasonable. I wouldn't put it in an uncontrolled warehouse in Arizona or anything that may get too hot for it, and then you would see some oxidation. But as long as those things are kept within reasonable range, I'm saying your normal lab environment, I don't see a big issue. But again, can you do that? Maybe your manufacturing setting is more of a warehouse, and then we would want to monitor temperature and humidity a little bit more closely and relate that back to possible degradation.
Would they need to worry about UV lights or potentially vacuum sealing to minimize oxidation?
Vacuum sealing is never a bad idea. That certainly keeps most things out. Depending on the polymer material that you're vacuum sealing with, it has barrier properties. So thinking about that as well. UV, I guess this sounded like it was implanted in something else. So the UV is definitely going to hit that top surface of the polymer, and that can be an issue for many different polymers. And if it's definitely going to be in UV, then we want to talk about stabilizers that you can add to the polymer that scavenge those free radicals as you get photooxidation. So if it doesn't have those included and it's definitely going to be sitting in UV, I think that's something that we can take care of in formulation, and we need to think about and test for as well.
Great,
QUV
thanks.
cabinet is a good way to test for UV photooxidation.
Awesome. Okay, next question. For medical devices that have polymers or other materials in contact with the skin, that's past ISO 10993 requirements, is a non-toxic certification enough for the FDA, or does the material need to be tested?
So that it depends on what predicate um, information you have. So if you can show that that same material has been processed the same way and came back with good results with something that's already out there, um, then you don't need to do it. ISO 10993 has about 12 different parts to it, and depending on what your medical device is, you may have to run, section 5 or section 12 of it to show biocompatibility. Um, I guess another part of it um, is that the FDA will ask you if you have a new material that no one's used before, or if the material is processed in a new way. They definitely will ask you for that 10993 data from your exact part. So again, it comes down to the FDA realizes that polymers are ever changing, and they want to ensure that the way that you're processing it doesn't make that change to an already certified, I guess they're not certified, but a polymer that's already been used in other devices and processed differently may pass, whereas yours, if you're going hotter on the processing or longer time, that could cause degradation, and you could get some molecules coming out of that then they have to worry about bio compatibility. So that one's, the answer is it depends quite a bit, but a lot of times the FDA will make you do your own testing for that.
Okay, I have one more that came through, and it's something we hear from actually a lot of companies. Time short. So how much time can accelerated aging actually save in the timeline and the process?
Yeah, that's a good question. So um, it depends which testing we're going for. So I guess I'll go with the ones that you can accelerate the most first. And those are the creep and stress relaxation tests, and the frequency-based one too, where we can use time temperature superposition to get years of what that polymer should do is probably going to do, in a short amount of time, a week. So you're taking a week of data and you're spreading it out into years. The other one that can be fairly quick is environmental stress cracking. So if you know what chemicals you're going to put in contact with your device, then we can increase the temperature. We can increase the concentration of the, say maybe it's a disinfecting agent, a quaternary ammonium salt. We can increase the concentration of that. And we can increase the strain. Instead of putting the strain that your device is going to put on the part, we'll double that. And all of those things can really increase to show if it's going to fail or not. If you can pass at an accelerated rate, then you could certainly pass at your normal rate. Now, the last one is maybe your more typical accelerated aging program, where you're taking a whole device and you're putting it in an oven at maybe 40 or 50 degrees C. And in this one, you can't accelerate too much. It usually follows an Arrhenius type equation, and different polymers degrade at different rates. So having some model that we can show and relate back to how fast it's aging by aging at different temperatures, we can actually prove how fast it's aging. And for that, I'd say the fastest I've seen is about 8x. So if you need to show that your product has to last for a year at 25 degrees C, and you can get an 8x increase by going to 50 or 60 degrees C, then you'd be aging it for a month and a half, and that would tell you that it would last for a year. So that's the more typical accelerated aging timeline. But as I said, it depends on the testing and the geometry and the environment of your particular device.
Great. I think that's all the questions we have, and actually that's perfect because we're right up on time. So Jeff, I just want to say thank you for pulling this all together. This was incredibly helpful. I know that was a ton of information. And anyone in the audience, if you'd like to reach out to Jeff, obviously, jellis@ewi.org. If you have any questions, you can also contact me, Rachel@massmedic.com, and we'd be happy to get you a copy of the video. And I believe Jeff said there will be a copy of the slides that we'll be able to share with you as well. So thank you, Jeff, and thank you to EWI. This was incredible, and I hope to see you all again very soon.
Thanks for having me, and thank you everybody for joining.
Have a great rest of your day, everyone. Bye-bye.
Bye.